Yeah, I want to talk about what's going to be coming up here as we approach the end of the semester. Okay, so we have all of next week and then a Tuesday after that, as far as the class goes, right? We have our 2 classes next week and then the Tuesday of the week after that. It's 3 more classes after today, right? Everybody looks surprised. Right? That's it. 3 more classes. Okay? Here's what I think we should do, propose that we do. I have given you a problem set due next Friday. That'll be the last official one. I think there'll be an extra credit one due probably at the time of the final for those that wish to earn some more points and to get a little more practice. It will be on chapter 7, which will be the last chapter we will look at. Okay? But this is the last official problem set. Okay? Due next Friday. I think we'll just not do a quiz next Thursday. Okay? And continue talking. I want to get as much into chapter 7 as I can because that's where things really get interesting. Okay? Where we will study systems that you have to do what's called a full quantum mechanical analysis of the system, which boils down to worrying about whether the particles you're studying are what are called either fermions or bosons. Okay? So that will be the topic of chapter 7, and we're going to start chapter 7 later today. So that's what I propose. This being the last official problem set, no quiz next Thursday, and then there'll be an extra credit problem set, and we'll be due, I think, when you do the final, which our final is Monday, May, I believe 7th is the date. Okay. Monday. It's definitely Monday. Okay. It's a morning. We'll talk more about that next week. Okay, does anybody have any questions on anything I've said? No? Okay, so we're going to finish chapter 6 today, and then we'll start chapter 7. Let me remind you where we were on Tuesday. We were right in the middle of a pretty important calculation. We were doing a statistical mechanical analysis of an ideal gas, dilute gas, so the particles are non-interacting. They're identical particles. We were saying, let's assume we're studying a gas of nitrogen molecules, N2 molecules. So every particle is identical. It's the same molecule, N2, but they're dilute. So the wave functions for each molecule don't overlap a great deal. Right? And when you are in that kind of a situation, you can do what's called a semi-classical analysis. That is, in essence, exactly what we're doing right now. Okay? And so what we did is we said, okay, in the canonical formalism, the first thing we do, the main thing we do, is find the partition function. We have an n-particle system. They're not interacting, but they are identical. So the partition function for the whole gas will be the partition function for one molecule raised to the n power, because they're n molecules. But then I have to divide by a factor of n factorial to account for the fact that they're all identical. And then I have broken, so I then said, okay, now I'm going to focus on calculating what I call Z1, the partition function for one nitrogen molecule. And then I further broke that down into subparts and saying Z1 is a product of 2 separate Z's. One partition function for just the translational motion, and then another partition function for what we're calling the internal motion, which accounts for the rotation of the molecule and the vibration of the molecule. And then I broke down, so then I said, okay, now I'm going to focus on just the translational part of the partition function. And I further divided that down into 3 parts for the translational motion along x, and the translational motion along y, and the translational motion along z. Remember all that? Does that ring a bell? That's what we did. And we worked out the partition function for the translational motion along the x direction. Who's got it written down in their notes? Z for the translational motion along x. Lx, what does Lx mean? What about it? It's the x dimension of the box, the x length of the box. And you take L sub x and you divide it by what? L cubed, the quantum length. Then I had done, at the very end, I had done an aside where I mentioned that this quantum length is also known in other textbooks as the thermal de Broglie wavelength, and I made a plausibility argument why it's called that, because all you do is combine the de Broglie hypothesis between the wavelength and the momentum and the average energy in thermal physics, and you get an expression that is almost identical to this. So we're going to call this the thermal de Broglie wavelength or the quantum length. So we can label it as LQ or lambda TH. They mean the same thing. And that's the expression. And I said you can think of that as being roughly the size of one of your molecules at a given temperature T. That's like the extent of its wave function. Okay? Then I mentioned a useful rule of thumb. You can do a semi-classical analysis, what we're doing now. Whenever the thermal de Broglie wavelength, i.e. quantum length, is small compared to the interparticle separation. Okay? And then I drew a little picture of the molecules as little clouds of diameter LQ or lambda TH. And then I had the distance between neighboring clouds, wave functions, being equal to the interparticle separation, which is the total volume of the box divided by the total number of molecules to the 1/3 power. And I had the size of the molecules being small compared to the distance between nearby molecules. That's the situation I'm imagining we're in now. Okay? However, the converse of that rule of thumb is this. If the quantum length, also known as the thermal de Broglie wavelength, is comparable to or even larger than the interparticle separation, then you've got to do a full quantum mechanical analysis, where you have to worry about whether or not the particles you're studying fit into the category called fermions or the other possible category called bosons. That's what we're going to study in Chapter 7. Okay? To give you a sense of when one kind of analysis, semi-classical, versus the other kind, fully quantum mechanical, is needed, based on this kind of inequality, let me make a little table where we look at several different example systems, the mass in kilograms of the particles that make up that system, a typical temperature at which you study that system, the quantum length or the thermal de Broglie wavelength in meters for such a system at a given temperature, the interparticle separation in meters for such a system, and then this ratio, which will be dimensionless for such a system, and that will tell us if we have to do a semi-classical analysis or a fully quantum mechanical analysis. So one system is air in a typical room. That's basically what I'm taking this aside right now, but in studying an ideal gas of nitrogen, that's the predominant constituent of air. Okay? So the mass here means the mass of one of your particles. Well, that would mean the mass of a nitrogen molecule. 4.7 times 10 to the minus 26 kilograms per molecule. Let's say it's the temperature of a warm room. Let's use a nice round number, 300 Kelvin. Then we can calculate the quantum length, also known as, remember, the thermal de Broglie wavelength, lambda TH, by using that formula right up there. H over the square root of 2 pi m kVt, and what you get for the quantum length, or the thermal de Broglie wavelength, of air at room temperature is 1.9 times 10 to the minus 11 meters. Now the typical interparticle separation for air, which you can just get from the ideal gas law, is 3.4 times 10 to the minus 9 meters. 3.4 times 10 to the minus 9 meters. So this ratio of lambda TH over V over n to the 1/3 for air in a typical room, 0.006. So the ratio is pretty small compared to 1. A semi-classical analysis is fine. Okay? What if we study not, in essence, gaseous nitrogen, but liquid nitrogen? Okay? If you cool down gaseous nitrogen enough at atmospheric pressure, namely down to 77 Kelvin, you'll liquefy it. Okay? We'll take the same mass, because it's still nitrogen, but now the temperature is 77 Kelvin. The quantum length, or the thermal de Broglie wavelength, depends on temperature. And so now, inversely, by the way, on temperature, inversely, so lowering the temperature makes the thermal de Broglie wavelength, or quantum length, bigger. And now the quantum length for the nitrogen is 3.8 times 10 to the minus 11 meters. The interparticle separation for nitrogen in a liquid state is much smaller, well, an order of magnitude smaller, because it's in the liquid state. So the molecules are closer together. Okay? And it's about 3.8, get the right column, 3.9 times 10 to the minus 10. So it's an order of magnitude smaller. And now, the key ratio here on the last column, 0.1. Okay, still less than 1. So probably okay to continue with the canonical approach, like we're learning in this chapter. What if you study a different material now, but at a very low temperature, liquid helium? Okay, specifically the most common isotope of helium, helium-4, with 4 neutrons in the nucleus. Then the mass of a helium atom is 6.6 times 10 to the minus 27 kilograms, helium atom. The temperature to liquefy helium, 4 Kelvin. So now we're going to have an even larger quantum length, 4.4 times 10 to the minus 10 meters. Interparticle separation, well, it's still liquid. It's very close to the same for liquid nitrogen, 3.7 times 10 to the minus 10 meters. And now this key ratio in this last column is 1.2. So you are going to have to do a full quantum mechanical analysis of liquid helium in which you treat each helium atom as a boson. We'll learn about that in chapter 7. Let me give you one more system. The quote-unquote gas of conduction electrons in a metal, specifically copper. Okay? Copper consists of a huge number of free electrons rolling around called conduction electrons, often modeled as a gas of electrons. Of course, the mass here is 9.1 times 10 to the minus 31 kilograms. It's an electron we're talking about. The copper is at room temperature, so we're back to 300 Kelvin. But our particles have a tiny, tiny mass. And the quantum length Thermal de Broglie wavelength depends not only inversely on the temperature, but also inversely on the mass. So we expect to have a pretty large quantum length, relatively speaking. 4.3 times 10 to the minus 9 meters. And it turns out the interparticle separation for the conduction electrons in copper is 2.3 times 10 to the minus 10 meters. So with this last column, this key ratio is 19. So if we want to study the gas of conduction electrons in a metal, any metal, not just copper, but I took that to be specific, we're going to do a full quantum mechanical analysis where we treat every electron as a fermion. And we'll learn in Chapter 7 how to do that. Okay? All right, this is really where I want to end that aside that I had started. Okay? Okay. Now back to the system we're studying, which is the top row in this table. Air in the room, i.e. specifically N2, a gas of N2 molecules. Okay, so we wrote down the partition function for the translational motion along the x direction. It was L sub x, the particular x dimension of the box that contains the gas, over the quantum length, LQ, right? So I claim that we can now just write down the partition function for the translational motion in all three dimensions, like that. Just take each possible dimension independently, and when you calculate the partition function, well, there's what we got for the x motion, Lx over Lq. So you can see what we're going to get for the y motion, right? We're going to get the y dimension of the box over the quantum length. And for the z contribution, we're going to get the z dimension of the box's length over the quantum length. Of course, what's the numerator when I multiply all those three together? It's the volume of the box. Let's just call that big V. That's the volume of the box containing the gas. And downstairs, well, we'll have the quantum length cubed. How about we call that the quantum volume? Okay? So little v sub q. So by that we mean the quantum volume, which just means take the quantum length and cube it. What would that expression be symbolically? Well, you can see up there the symbolic expression for the quantum length. So cube that, and you're going to have Planck's constant cube over 2 pi mass of each particle, kBt, to the 3/2. Okay? Okay, so we've got the partition function for the translational motion for one nitrogen molecule. So now I want to go back to getting the whole partition function for a single N2 molecule. So I'm going to go back to equation 1, which said that the partition function for the whole gas, Z, is 1 over n factorial. Take the partition function for any one molecule, Z1, and raise it to the n power. Okay? That's what we're headed back towards. Okay? But we're not quite ready to go to all of this because we're not finished with Z1 yet. Okay? What's the rest of Z1? So let's focus on getting Z1 finished. Z1 has two parts. The contribution from the translational motion multiplied by the contribution from the internal motion. Remember, Z internal comes from the rotation and the vibration. I will remind you that we've actually already dealt with both of those cases. in earlier work. Okay? We've dealt with oscillators a lot. And I already worked out the case of a rotating diatomic molecule in the canonical formalism in chapter 6. So we've actually already done these. We just got to kind of group everything together. Okay? So let's so I've got the Z translational done now. Let me make sure I have the numbers yet. Okay. But that's it. That's Z translation. So now we're going to focus on Z internal. Okay? So now let me remind you of things we already knew. Okay? So for the rotational part, Z rotational. I'm going to sum over the states, the Boltzmann factor for each state, e to the minus beta times the energy associated with rotation. And that boiled down to summing over the angular momentum quantum number little j, which can run from 0 to infinity. There was a degeneracy factor of 2 times little j plus 1. And then the Boltzmann factor is e to the minus beta times the quantum of rotation, e root. This ring a bell? Where, e root times j plus 1. Okay? Where, or epsilon root, I should say. Epsilon rotational is h bar squared over 2I, where I is the moment of inertia. Okay? I'm writing that down fast because I did that already. Okay? In chapter 6, we studied rotation of a diatomic molecule already. Okay? Let me remind you of some numbers. This is just a constant. Remember, I've got a specific system, N2. So for an N2 molecule, you can find the rotational inertia. Of course, you know Planck's constant. The h bar, remember, means it's h over 2 pi. And you discover that this is, to 3 sig figs, 0.246 millielectron volts for the quantum of rotational energy. I found it useful to define just a new constant. Think of it as a dimensionless temperature scale, little t rotational, as kb big T over epsilon rotational. Think of it as just a dimensionless temperature. Okay? You can also think of it as 1 over beta times epsilon rotational. Same thing. Okay? If I do that, then my rotational partition function is the sum over the angular momentum quantum number, j, going from 0 to infinity, the degeneracy factor, 2j plus 1, times e to the minus j times j plus 1 over little t rotational. Okay, now we spent some time before talking about this partition function. Right? Of course, our desire with any partition function is to be able to do the sum completely, analytically, exactly. Just do it. Right? Either because it's already a known sum, like a geometric series, which this unfortunately isn't, or it might be valid to convert the sum to an integral, and then do it as an integral. Unfortunately, you can't do either with this. There is no closed form analytic expression. So what you have to figure out is just how many terms are important. Because eventually, as you go higher and higher in J, this exponential gets more and more damped, smaller. And so the terms make smaller and smaller contribution. So at some point, you can just terminate the sum. But how far up you have to go depends on what the temperature is. Okay? So one thing that's very handy is, in order order to know how far you have to go on this sum, how high do you have to go with the little j, is to ask yourself this question. Okay? At what temperature, capital T, is the dimensionless temperature, little t rho, basically 1. And that's not hard to find out, because you know the number for epsilon rho. So put a 1 here, put the known number here, put the value of Boltzmann's constant, solve for the actual temperature, capital T, you discover that that's 2.84 Kelvin. Why is that helpful? Because, of course, that's not a very high temperature by our daily standards, okay? But that's what it is. So here's what you know. If the temperature of the gas, again, don't worry about the fact that, well, actually it would have liquefied by now, okay? Suspend that thought for a little bit. If the temperature is small compared to that, 2.84 Kelvin, the actual temperature, then the T rho is small compared to 1. The dimensionless temperature, T rho, is small compared to 1. If this is small compared to 1, then that's small in the denominator, right? That makes the whole thing here big, but it's e to the minus big, so that's nothing, right? Small. So the only term that's going to contribute in this whole sum is j equals 0. Because that'll be then e to the 0, which is 1 times 1. 1. The partition function will be 1. If the temperature is low compared to that. Once the temperature is comparable to that or bigger, then more terms in here become important. So how many terms you have to use just depends on what the temperature is. So I thought it might be helpful, I haven't had a chance to load this file, so I'm going to put this thumb drive in here. I thought it'd be helpful to show you this phenomenon. So I went to Mathematica, and I just made a little manipulate file. And so I'm going to plot the partition function, well, the terms in the partition function. This stuff, right here, versus J, and then I'm going to be able to vary the temperature. So let me show you what I plotted. I have to say yes, of course, because I've written so many. It is easy. Once you get used to it. I guess that's true for almost any programming language, right? Yeah. Once you're used to it, you say, oh yeah, that's easy. Computer. Okay, all right, now, very basic little program. And it's actually, I mislabeled this. I made this in a hurry this morning. It's not zero I'm plotting. It's the argument here inside the sum. Okay? As a function of j, where j can be 0, 1, 2, 3, 4, 5, and of course it goes, j goes on, but I stopped there. You'll see why. And then up here's a slider that lets me vary little t rotational, the dimensionless temperature. And notice by default it's 0.1. So it's small compared to 1, so that's what I would call the low temperatures limit as far as rotation goes. Remember, I argued then that the partition function will be 1, and that will come only from the j equals 0 quantum number. And there's, on the quantum number axis, there's j equals 0, and there's the contribution, see the value is 1. And all the other contributions from J, like J equals 1 and J equals 2 and J equals 3 of this, are so small they're down here at 0. Then all I have to do is drag that slider to make the temperature higher. Okay? All right? And if, as I do, you will find that J equals 1 will start to make a contribution as the temperature goes up. And then J equals 2 will start to play a role as the temperature goes up even more, etc. Okay? So now we'll just raise the temperature. Now J equals 2 is important. Now, oh, J equals 1, I mean. Now J equals 2. Now J equals 3 starts to play a role. Just making the temperature go up. Now J equals 4. Right? So, depending upon what the temperature is, that's going to determine how many terms you have to use in that sum. Okay? Alright. But you do know this. If you were in the low temperature limit, little t rho small compared to 1, it's only that one. Okay? Okay. Alright, so that's what I want you to see about J rote. And that's all we can say about J rote. But there's also the vibration of the molecule. Okay? So we'll have a Z. Z rote we'll have for the rotation, and now we'll have a Z VIB for the vibration. Okay? Z vib. We've done that one already. And the good news there is that partition function can be summed exactly. We've done it already. It's a geometric series. Okay? So for the vibrational motion, Z vibrational will be the sum over the quantum number label for the simple harmonic oscillator states. We tend to use the symbol N for that. So N going from 0 to infinity of the Boltzmann factor, okay? E to the minus beta epsilon vib times N plus a half. Remember that? Where epsilon vibrational is our old friend h bar times omega, where omega is the angular frequency of the oscillations. You can find out what that omega is for N2. I'll tell you. It's 2 times 10 to the 14 radians per second. That would be measured. And so, h bar times omega turns out to be, for N2, 0.132 electron volts. Electron volts, not milli electron volts, but electron volts. So about 3 orders of magnitude bigger than the epsilon rotational. Okay? Alright, now, we'll do the same kind of thing I did over there for the rotational motion. Let's define a dimensionless temperature for the vibrational motion as kBt over the quantum of vibrational motion, epsilon vib. And if you want to think of that as 1 over beta times epsilon vib, you can do so. And then you need to do that sum to get the vibrational partition function, and it's a geometric series. So we know exactly what the result is. Okay? Now, let me show you how we're going to write it. Sum n going from 0 to infinity, e to the minus n plus a half over t vib, little t vib, the dimensionless temperature. Note something. I can write this as 2 exponentials multiplied together. E to the minus n over little t vib times e to the minus 1 over 2 t little t vib. And I can bring the 1 factor, e to the minus 1 over 2t vib out front. It doesn't depend on n. Okay? And you know what? Then that's just going to get carried along for the ride out front. And everywhere where I'm going to end up calculating something measurable, that factor out front is going to end up canceling. I guarantee it. So I'm not going to worry about that e to the minus 1/2 over little t vib. Okay? I'm just going to say, let's write it like this. I mean, you can carry along that factor of e to the minus 1/2 over little t vib, and you will find that whenever you get around to calculating anything you can measure, like the internal energy or the heat capacity at constant volume, it will not show up. It will end up appearing in a numerator and in a denominator, and canceling. Okay? So that's what I just keep. That's the geometric series. Okay? And we've done that already, so I'm just going to write the answer. You need to be able to do this too. Just get to this, look at that and say, oh, I can immediately write the answer. Okay? It's 1 over 1 minus e to the minus 1 over little t vib. By the way, let's do the same thing we did over here. Let's ask, at what temperature, big T, is little t vib, let's just say, is equal to 1, right? At what temperature, big T, is little t vib equal to 1? Okay. Answer? You see how you would answer my question? You would go over here and put 1 here. You put in the known value for epsilon vib, the known value for kb, you can find out what capital T is. You discover it's 1522 Kelvin. So if the temperature of the gas is small compared to this, all right, then little t vib is small compared to 1. And small compared to 1, well, small in the denominator makes that whole thing big, but it's minus. Right? So they get suppressed, so the only term that would be important is n equals 0. Because that's just e to the 0, which is 1. So in the low temperature limit, this z is 1. Where low means that little t is small compared to 1, or big T is small compared to this. And only when big T starts to get of the order of this will terms other than just the first one start to be important. Okay? You can also see that by looking at this. When little t vib is small compared to 1, low temperature, all right, then that's 1 over small, which is big. That's e to the minus big, which is negligible. So 1 minus negligible is 1, and 1 over 1 is 1. Okay? So at low temperatures, this is basically 1. Constant. Okay? Only when you start to get temperatures about that big is this going to start to get interesting. So you need to know the temperature scales at which the particular partition functions start to become important. Okay? All right, so with all that information in mind, we're ready to write down, well, it'll look pretty simple, really, in terms of symbols, but we're ready to write down our partition function for nitrogen. 1 over n factorial, z for one molecule raised to the n power. That's 1 over n factorial. Okay, z for one molecule is z for translation times z for rotation times z for vibration. Okay? So I'm going to write that like this. Big V over the quantum volume, that's the translational part, times z rotation times z vibration. And this is all raised to the n power. That I'm going to number equation 2, or 3. Did I have a 2 already? I should have.
Yes. There is a 0. But that was from this one. There was Tuesday.
Yes, it would have been from Tuesday. Okay, so this is 3. Okay? Now I have the partition function for the whole gas. Everything follows from that. So, D, let's start calculating thermodynamic quantities. Like the total energy, also called the internal energy, U. That is, remember, in terms of the partition function, negative 1 over the partition function, z, partial of z with respect to beta. Which is also the same as negative partial with respect to beta of log z from the chain rule. Where, from equation 3, let's write down what log z looks like. Because that's what I'm going to use, log z. Well, just go to equation 3 and take the logarithm of both sides. And log z, okay, well, there's going to be a minus log of n factorial from that, because it's in the denominator. And then all this is raised to the n power, so when I take the log of that part, it's going to bring the n down. So I'm going to have n times, and then I got the log of all this stuff multiplied and divided. So I can break that up into separate terms, like the log of the volume of the box, plus the log of z rotation, plus the log of z vibration, minus the log of little vq, quantum, volume, close bracket, and then minus log of n factorial. Okay? Anybody think what we're going to do with this term? Log of n factorial? Sterling. Okay? The log of n factorial is n log n minus n. So we're going to use that for the log of n factorial. And then we will have, I'll just continue right here, log z equals. All right, now every term is multiplied by an n, so there's going to be an n out front. N, open square bracket, log capital V, plus log z rotation, plus log z vibration, minus log little vq, minus log n, plus 1, close square bracket. Right? Where these last two terms with the n out front come from the Stirling approximation. Okay, I'm going to number this log z expression, the equation. So now, let me calculate, or write down an expression for, the internal energy of the gas, the dilute gas of nitrogen molecules. So U will be, okay, well, minus the partial with respect to beta of log z. Log z is given by equation 4. Okay? So I'm going to take the partial with respect to beta of what you see right here and slap a negative sign in front of it. Now when I do that, notice there's going to be an n out front. That's just going to get carried along. So I'm going to have out front a minus n. And then I just take the partial, go down the line, and take the partial term by term with respect to beta. Beta, of course, is 1 over kBt. So the terms have to depend on temperature to have any non-zero derivative. So that doesn't have any temperature, it's just a V. So that doesn't survive the differentiation. These partition functions depend on temperature, right? So those survive. I'm just going to keep them, I'm going to write them like this. Partial with respect to beta of log Z rotational. And then the next term will be partial of log Z vibrational with respect to beta, because this is going to depend on temperature. All right? No temperature dependence here, no temperature dependence here. But there's temperature dependence in the quantum volume. So there'll be minus partial log little VQ with respect to beta. That's equation 5. All right, now the term I'm most interested in is this one, right here. Okay? Because that's pretty easy to figure out. So let me show you what you do here. So a little reminder, VQ itself is h cubed over 2 pi m kBt all to the 3 halves. Okay, we've written that down already. I'm going to write it like this. H cubed times beta to the 3 halves all over 2 pi m to the 3 halves. Right? Same thing. Now let me take the log of both sides, because I have to have a log of little VQ. Okay? The important part when I do the log is the part that depends on beta, because that's what I differentiate with respect to. So I'm going to look at that part and say, well, when I do a log from that, I'm going to get a factor 3 halves log beta. And then I'll have all this other stuff inside the log. Log of h cubed over 2 pi m to the 3 halves. Because that's not going to be important. And now I can take the partial of log VQ with respect to beta, because there's the beta dependence. So this is going to be 3 halves partial with respect to beta of log beta. 1 over beta. But beta is 1 over kBt. So this is just 3 halves kBt. We knew we had to get that for the translational motion, right? 3 degrees of freedom, 1/2 kBt of energy for each degree of freedom. 3 halves kBt. But look how it came out of the formalism. Okay? So then, oh, by the way, if you want, I'll talk about this one, but it's not terribly interesting. You can do that derivative too, yes? Because we worked out Z vibrational exactly. Right there. Yes? You can write it in terms of beta. You can take the log of it. And then you can take the partial with respect to beta. Right? I'll write down what you get when you do that. You get epsilon vibration. 1 minus e to the beta times epsilon vibration. That's not a typo. There is no negative sign there. Okay? That's the expression you get for the vibrational energy. It's going to be unimportant, though, unless the temperature of the gas is really, really high. Okay? This one you can't do anything with analytically. You're going to have to treat it numerically. I'll show you how I dealt with it in a different mathematical program in just a minute. So with all that said, let's write down our symbolic expression for the internal energy of the gas. U equals. All right, so so you see where I've got a minus n times the partial of log z rotation with respect to beta. That all together is, I'm just going to call u rotational. So by that I mean minus n partial log of z rotational with respect to beta. That's going to be u rotational. Then the minus n times partial of log z vibrational with respect to beta, which is that, that's going to be u vibrational. Then, look, I have a minus n times minus partial of log little vq with respect to beta, partial of little log little vq with respect to beta is 3 halves kBt. So a minus and an n, so plus 3 halves n kBt. And you've got the internal energy in a symbolic form. This, you can see what you would write down for that. This, you can't write down a closed analytic expression. It depends on what the temperature is. But I will go one more step. They'll say, how about the heat capacity at constant volume? That's an easy one once you have the internal energy. Take the partial of the internal energy with respect to temperature, constant volume. That means take equation 6 and go right down the line and take the partial with respect to temperature. So that's the partial of u rotational with respect to temperature, plus the partial of u vibrational with respect to temperature, constant volume, plus the partial with respect to temperature of that term, 3 halves n kB. Why don't I show you how I did that? That'll be a good place to take a break after that. All right. This is a PDF of a Mathematica program I wrote that shows you how I dealt with equation 6, and then basically what I wanted was CV. Because I want to plot CV as a function of temperature for the nitrogen gas based on our analysis. Okay? So, I defined a function, z rotational, as a sum over little j, 2j plus 1, e to the minus j plus 1. Okay? Now this is little t rotational, where I put in numbers for constants. Okay? So that I could write it in terms of the temperature. Notice I just took an arbitrary but high upper limit to just terminate the sum. I know I'm well above any term that, well above any j's that are going to contribute to that sum. Okay? Mathematica won't, I can give Mathematica a large number up here, it's fine. So then what's the average energy due to rotation? Right there. Okay? Except I'm dividing by n. I did, though, to change it to a derivative with respect to t, not beta. Then you got to do the chain rule, right? You got to change a partial with respect to beta to a partial with respect to t, doing the chain rule correctly, and you'll end up getting, you get a factor of Boltzmann's constant, t squared, the partial of log 0 with respect to t. Okay? So that's that's u rot over n. U rot over n, right there. Here's the vibrational partition function. Yep, exact result. Where I put in numbers for the constants. Okay? Exact result. So here's how I would get the average vibrational energy. That would be that term, but I'll divide by n. And I'll do the derivative with respect to t, using the chain rule. So I get Boltzmann's constant, t squared, the partial of log z vibration with respect to t. I guess I was lazy and didn't want to do that derivative myself. Okay? Because I just told Mathematica to do that derivative. Then the heat capacity at constant volume is, well, 3 halves nkb. I'm going to divide by n. So 3 halves kb, that's right there. So that contribution comes from translation. plus the partial of the average vibrational energy with respect to temperature, plus the partial of the average rotational energy with respect to temperature. So, there. And so I've now got a function of temperature that Mathematica is more than willing to evaluate it at a whole bunch of different temperatures. And then I can make a plot of the heat capacity as a function of temperature. I asked it to do it on a log linear plot, horizontal scale being logarithmic, so that I could get many orders of magnitude visible. So the temperature on the horizontal axis in Kelvin, going from 0.1 to 1 to 10 to 100 to 1,000 Kelvin. Okay? And I did CV over NKB. And this is the result you get, which is like what you would see in your book. Okay? Now before, we used to just be able to say, well, how many degrees of freedom? And then use the equipartition theorem. And so using before, we could get a flat part here, and a flat part here, and a flat part here. But we couldn't use the equipartition theorem to get these smooth parts that connect between those plateaus. And now it comes out automatically. The behavior that we expect comes out automatically. The only behavior we don't get out of this is that I didn't go low enough in temperature to see this eventually go down to 0, which it would do. Okay? But it's got to be a pretty low temperature before that would happen. In fact, I estimated how low that would be. It would be something like, I think it's like 10 to the minus 17 Kelvin before this would go down. So that would be 16 more orders of magnitude going to the left before it would finally drop down. Okay. So that's pretty powerful. We finally got that graph that we've seen pictures of earlier in the book. You even see pictures like that in intro physics books when you're studying thermodynamics. Now you know how you could actually calculate it. Okay? By the way, I know you want to take your break, but this is, we say these last couple more points and then we'll be finished with chapter 6. Everything follows from the partition function. Once we had equation 3 for Z, we got U, the internal energy, CV, the heat capacity. We can get next, just write it over here, we can get the Helmholtz free energy, F, because that's minus kBT log Z. So what we're going to do is use the equation 4 that I just erased for log Z and slap on a negative kBT in front of it. You can get the pressure. The pressure is the negative partial of the Helmholtz free energy with respect to volume at constant T and N. You want to try that for yourself. Construct F. All you do is take our equation 4 for log Z and multiply by a negative kBT. That's F. Then take that F and do this operation to get the pressure. Understand what I'm saying? That's good practice for you. Take the expression for F, do that partial, slap a negative sign in front of it, and that'll be the expression for the pressure. Guess what you get? What do you think you'll get? You'll get NKBT over V. Ah, we have to, yes? And that is what you will get. You can also calculate the entropy of this diatomic ideal gas, yes? Can't just go to the Soccer-Tetrode equation, say, I don't need all this, I can just go to Soccer-Tetrode. No, that's for a monatomic ideal gas. This is a diatomic. So how are you going to get the entropy? It's the negative partial of the Helmholtz free energy with respect to temperature at constant V and N. So use the F that I'm telling you you should be able to get from equation 4. That's in one of your homework problems. You can get the chemical potential for a diatomic ideal gas by taking the partial of the Helmholtz free energy with respect to the particle number n at constant T and V. That's also in your homework. Okay? Everything follows from Z. All right, so that is the semi-classical ideal gas. That is as exact as you can be. All right, so there's where we will pause. We'll come back and we'll talk a little while about how you deal with systems that are fully quantum mechanical. Okay? And what that means. Okay? So we'll take our break.